Listen harder.
It really is on. It's as loud as it gets.
David, listen harder. I have something for him too.
Okay, presentation tonight being given by Dave Bailey. He's a club member, well known to us for giving challenging, sometimes perplexing presentations. And if you thought you were starting to understand it, he'll sprinkle some physics in there to take care of that for you. Anyway, Dave is going to be talking about radiation on young Earth-like planets tonight. He's going to bring up cosmic rays, carbon-14, radioactivity, sunburns, and sunscreen. The recommendations for branding today. Photosynthesis, vision, potassium-40, and program death will also be discussed. Dave said that he was into astronomy before he was born, since his parents met at the Yerkes Observatory in the 1930s as grad students. So he was kind of before he was born. He's also studied under Carl Sagan and other leading astronomers at Harvard.
Jealous.
So that's worth an autograph for him for just being close to Carl Sagan, I guess. Take it away,
I have
Dave.
an important question to ask. Who doesn't have one of these and wants one? This is the last one. I've been trying to hand out pairs to pairs. This one can count into a family. Okay, you got it.
Should you use a microphone?
He doesn't need it.
All right. This is a little bit unusual. My topics, my presentations usually have a topic. This one has a bunch of topics. I like questions in real time, because if I ask you to wait till the end, you'll forget what your question was. So don't be afraid to interrupt me. If I think that you and I are the only two people interested in that question, I'll say, see me later at the restaurant. Okay. Let's start with cosmic rays. It's one of the major sources of radiation on a planet, at least in our solar system it is. Basically, all the incoming cosmic ray particles hit nitrogen or oxygen molecules on the way in. And so what we detect at ground level, like with Geiger counters and other more sophisticated detectors, is secondary particles that were as a result of collisions way up there. Sorry about that. That's fine. That's one kind of cosmic ray radiation source, is the secondary particles that come down. Another source is called spallation products. Spallation is a fancy word for chipping. And like if you have a poor innocent nucleus here of, let's say, N14, and here comes a cosmic ray that goes splat through there, and a whole bunch of other things go splat and get kicked out, then this thing is no longer a nitrogen-14 nucleus because one or more protons or neutrons have been kicked out of it. So this thing is called a spallation product. And sometimes one of the things that comes out here might be, let's say it's a hydrogen-3, the tritium nucleus. That is also considered a spallation product because it's something of interest, and it's a chip that was knocked out of the nitrogen-14 by the cosmic ray. Third source is when neutrons get kicked out here. There's a neutron, there's another neutron. What happens to those neutrons? Well, we'll find out shortly. They're interesting. And you expect that this neutron thing is going to be very complicated. Turns out almost all of them, almost every one, makes a carbon-14 nucleus. How in the world can that be? We'll find out. I'm going to the second page here. The little chart at the upper right looks at the 10 molecules that are found in upper air. There's really only 10. Well, 10 nuclei. Carbon-12 nuclei, 12 carbon-13 nuclei, all found in CO2 molecules. Nitrogen-14 and nitrogen-15 found in nitrogen molecules. Oxygen-16, 17, and 18. And argon 36, 38, and 40. And that's it. Everything else, all the other molecules found in the upper air, really high up, are so rare that they're not worth thinking about. Down at the bottom of that chart there has total target area, which basically says how many of this particular kind of nucleus found in this particular kind of molecule, how many are going to get hit by cosmic rays. And you can see, for example, over in the right-hand, lower right, argon-40, for every 1,000 hits, well, it says 1090, call it 1,000, for every 1,000 hits on argon-40 nuclei, there's going to be 90,000 hits on nitrogen-14 nuclei. Interesting to know. Then what happens after those hits? Well, at the lower left, we've got all possible spallation products. And there's 202 different kinds of chips that can come out of these collisions. But almost all of them are of little interest to us because they either are radioactive themselves and will decay very quickly into something else before they have a chance to get down to the Earth's surface, or maybe they're stable isotopes. And by the time you're done winnowing them out, you've got 13 left. And you can see the 13 I've listed there, and they have different half-lives. The slowest one has a half-life of 1.5 million years, it looks like. The fastest one I've listed is 2 weeks. I claim anything that has a half-life of less than a week, you're never going to see it at the ground level, because it takes some time for weather processes to bring those radioactive nuclei down to the ground. And if it has a half-life of like a couple of days, you'll never see them at the ground. And it will decay to something else by the time they have a chance to be at the ground level. The lower right of, this is page 2, I show some possible spallation reactions which can produce those radioactive, cosmic produced, spallation nuclei. And I'm going to skip over that pretty much. If we have time later on, I'm able to go into what that all means. The next page, what's this, page 3 or something?
You have like secondary reactions, because you have cosmic rays hitting like argon-40, going
Yes.
off into argon-37 plus 3 neutrons.
Yeah.
And then you can have cosmic rays hitting the argon-37.
Oh, those are 2 different reactions I've got. See,
Okay.
one has an underlined 1, bold 1 underlined, the other one is bold 2 underlined. So there's 2 different possible collisions.
All these reactions are...
Yeah. Some of them don't occur very often. In particular, look at number 15. Argon-40 gets hit, and what comes out of it is 10 different things. 3 plus 5 is 8, 9, 10. A sodium-22, 3 alpha particles, 1 proton, and 5 neutrons. Now, how often is that going to happen? Very rare. For one thing, how often are you going to get that exact combination of things coming out? And number 2, how often are you going to get a particle coming in that has enough energy to make that big a splat? Whereas, look at number 1 up the top. Argon-40 gets hit by something, and 1 neutron gets kicked out of it. That's going to happen way more often, because it doesn't take that much energy to kick out 1 neutron, as opposed to kicking out, what is that, 9 things coming out of that, the reaction number 15? And so reactions that look weird probably don't happen very often.
Yeah, but let me ask you, this is all caused by cosmic rays, right?
Yeah.
So the probability of a cosmic ray hitting argon-39, isn't it the same as for sodium or carbon-14? I mean, you still got cosmic rays coming down. And
The chart in the upper right tells you how often each of those hits are going to occur, because you got the 10 possible targets there. So in the upper right, you're looking at different kinds of targets, and then in the lower right, you're looking at different kinds of chip products.
I would think that the hit frequency would be the same, because cosmic rays are evenly distributed.
Well, the different
Well,
elements are larger.
Yeah.
Or
some of them are
atoms.
physically larger, so they're going to get hit more often.
Doesn't it also depend on the energy level of the cosmic rays coming
Yeah.
in?
Yeah.
As
Yeah.
to how
That's
how
right.
destructive the impact is going to end up being?
Later on, we're going to see a case where a cosmic ray can hit a nucleus and not knock anything out of it. And you say, why you might be interested in something like that? Well, it turns out, yeah, that might be interesting. We'll see later. Let's go back to page 3. Okay, we've covered the first 2 paragraphs of that already. When you look at the half-lives, back on the previous page, some of the half-lives are long, like 1.5 million years. Some of them are short, like 2 weeks. Don't make the mistake of thinking that the sulfur-35, I picked it as an example, 87 days, it must be decaying like crazy, whereas decays of argon-39, which takes 1,000 times longer, those decays hardly ever happen. Not true. Actually, every one of these product nuclei builds up gradually until the inventory of all of these nuclei all around the entire Earth is sufficient so that the decays occur exactly as often as the production collisions. In other words, things that have a long half-life, they just keep accumulating, accumulating, and accumulating, and eventually they're decaying fast enough so that they don't accumulate anymore. Yeah?
B is beryllium, right?
B is BE. BE is beryllium, yeah.
Oh, great, there's toxic heavy metal raining on us.
What?
There's toxic heavy metal raining on us.
Oh, no, beryllium is not heavy metal. It's one of the lightest metals there is. But it's way toxic.
Yeah, that's what I mean.
But bear in mind, this is going to come up later, so I want to mention it later. And that is that ignore all chemical toxicity when you're looking at radioactive materials. Because you could have the most toxic element in the world, like mercury. If you're being exposed to radioactive mercury, that's way worse than worrying about any chemical toxicity. Or it could be carbon-14. Carbon is in your body. You can't live without carbon. If you get an overdose of carbon-14, you're in trouble.
Yeah, that's true.
So radioactive toxicity trumps chemical toxicity every time.
Dave,
Yeah.
you were saying that, you just said that the production rate is equal to the decay rate.
Yeah.
Wouldn't that be assuming a constant flux of cosmic rays?
Oh, yeah. If for some reason cosmic rays are declared to be illegal tomorrow, and they stop hitting Earth entirely, then all bets are off. But that's not likely to happen.
Is the flux constant? Have we ever noticed?
We presume that over geologic time, the flux has changed a lot, because occasionally we've had a nearby supernova. When? We don't know. But if there has been a recent nearby supernova, you can bet that the production rate up there is way greater. It might be 100 times more for a while, for a few thousand years, maybe 1 million years, until we drift away from that supernova remnant. Where are we at? Okay.
Neutron bombs,
What are you looking at?
neutron activation.
Oh, yeah, neutron activation, yes. I'm going to skip over that part. Yeah, well, if you have a specific thing you want to talk about, we can. No, okay. Let's go to the first part of the second column there. What happens to the neutrons after they get kicked out here? I think that 98% of them stop short and 2% get down to ground level. That's a total guess on my part. It's an educated guess, but it's a guess. And it's not based on looking at numbers, just I think almost all of them will not reach ground level. That doesn't mean that they're not important for us, because they end up being absorbed by nitrogen-14 nuclei. So what happens, what helps some of them make it all the way down to ground level? Well, high energy, of course. A high-speed particle with more energy is going to go farther before it stops. Some of them are coming straight down. That's a small minority. Most of them are coming down at angles like this. You know? And the third one is ground level is pretty high in some places, like Tibet. Tibet is sort of in the same category as being a flight attendant on a jumbo jet. maybe worse because you're up there 24/7 instead of just during working hours. Okay, after the neutron slows down, it becomes what is called a thermal neutron. That means it's in thermodynamic equilibrium with the air molecules around it. And that in turn means it has a mass of a hydrogen atom, essentially. And that means it moves on the average as fast as a hydrogen atom let loose in air. And that turns out to mean about 1 mile per second. That's an extremely low energy. And it'll be different depending on the temperature of the air, etc. And those are called thermal neutrons. Thermal neutron inside the human body is moving a little faster because the human body is a little warmer than the air way up there. But in all cases, thermal neutrons means essentially zero energy. When we look at what happens to those thermalized neutrons, we'll discover that they tend to get absorbed by 3 different nuclei in air. One of them is N14, and one of them is argon-40. I'm losing my marker. And the third one is hydrogen-1. I'll find a different one. And those are the only 3. Just make sure that it will not, yes, it says dry erase. The reason why these 3 are the important ones is because of something called the thermal neutron cross-section. Some nuclei tend to absorb neutrons extremely easily. Some, the neutron just bounces off. Helium-4 has a thermal neutron cross-section of 0. That's not an approximate number. It's not based on how accurately we can measure it. It really is 0. No matter how you hit a helium-4 nucleus with a neutron, it always bounces off. In this case, the nitrogen-14 has a large enough cross-section, a cross-section of 1.9 barns. And that's the largest of these 3. And this is also by far the most abundant nucleus of these 3. You conclude that not over 99% of all the thermalized neutrons get absorbed by nitrogen-14 nuclei. Interesting. After the capture, an odd thing happens. Instead of remaining a nitrogen-15 as we might expect, the nucleus immediately emits a proton, turning into a carbon-14. Why? Now, we know nitrogen-15 is a stable isotope. Why does it decay? And the answer is, on the next page, what happens is 3 reactions occur. Tell me if I'm getting out of the picture. Actually, I'll erase there. We
I
have
think
an
he's
eraser?
got you.
We have an eraser? Yes.
There you go.
And anybody who has their handout open can see anyway. N14 plus a neutron goes to N15 star. The star means it's an energized nitrogen-15 nucleus. It's not the same as a regular nitrogen-15 nucleus. It's got extra energy. And what happens then is it decays in one of 2 ways. N15 star goes to carbon-14 plus a proton. And the other possibility is N15 star goes to N15 plus a gamma ray. And this decay is called the proton channel, and this decay is called the electromagnetic channel. And that just means saying electromagnetic channel is a shorthand way of saying that 4% of the time the nucleus decays by means of the electromagnetic force by emitting a gamma ray. Well, I prefer to say it by two words, electromagnetic channel. At one time I thought, electromagnetic channel? That must be something really sophisticated that I couldn't understand because I'm not a nuclear physicist. No, it's simple. So, where are we at? Yeah, this is, what did I say? I didn't say, but this is 4%. 4%, 96%. This thing is called the branching ratio. And again, once upon a time, the branching ratio, I couldn't possibly understand that. Well, 4% of the time it does this, 96% of the time it does that. There's nothing to understand. Why this is 4%, that I don't know, not being a nuclear physicist. I can make some guesses, but for our present purposes, just look at the fact that 96% of the time this goes to a carbon-14, which is very interesting. That's an interesting nucleus. And what happens to that nucleus? Well, eventually it gets incorporated into carbon dioxide molecules. Why is that? Because it ends up with a good kick because when it emits that proton, the proton comes out with a lot of energy, and the recoil means that its carbon-14 nucleus is hot, chemically hot, and it will fasten itself to the first molecule that it runs into, which is either a nitrogen or N2 molecule or an O2 molecule. And that means that there's four products. C14O2, C14O, which is a carbon monoxide molecule, C14N2, C14N. These three are all active molecules. They eventually get oxidized and you end up with 100% of that carbon-14 as CO2 molecules. Those get absorbed by plants. Plants don't like carbon-14. Somebody must have tipped them off that carbon-14 is a bad thing to have in your body because it's radioactive. But the plants just, they don't know anything about that. All they know is that they've evolved to prefer to take up carbon-12 and to a lesser extent carbon-13, and they don't like carbon-14, but they take up about the same amount of carbon-14 on a reliable basis, and that means you can date recent artifacts and anything recent that's made out of wood, either a fossil or something found in a pyramid in Egypt or something, and figure out what its date is. Basically, the date that you're looking at is the date when the photosynthesis stopped. Okay. Now, different other radioactive things from space, other things happen to them. Carbon-14 gets incorporated into wood. Beryllium-10, I assume, sticks to rock surfaces. Argon, radioactive argon, I assume dissolves in the ocean, or at least some of it does. So, yeah, just because we're looking at nuclear chemistry here doesn't mean that regular molecular chemistry doesn't apply. The plants make starch and sugar with radioactive CO2, and they don't care that the carbon is radioactive. They just do their thing chemically. So it's always a good idea to remember, just because we're focusing on nuclear stuff doesn't mean that chemistry doesn't apply, molecular chemistry. It does apply, but those are compartmentalized. Like one side of your brain is thinking nuclear, the other side of your brain is thinking chemistry. So I hope this quick course in nuclear physics has been a good introduction for you, or a good review. Introduction for some of you, review for others.
Let's back up to the cosmic.
Yeah.
So that obviously comes at a real intense energy.
Cosmic rays, yeah, they have large energy.
To rupture, you know, a carbon-14 like that, and
Yeah.
nitrogen, that takes a lot of energy to part
It does. But
Therefore-
cosmic rays vary, they probably vary by at least 1,000 to 1 in energy. And for every,
Each, it doesn't have a constant energy?
no, cosmic, they're all different. And some of them are just a proton, some of them are other nuclei. Occasionally they've found evidence that maybe it started out as an iron 56 nucleus. Those are extremely rare, of course, but if you get hit by a high energy cosmic ray with nitrogen 50, with iron 56, it's going to make a real splat. There will be cases where, instead of something like this happening, and there's a neutron of hydrogen 3, it gets hit by something sufficiently energetic. All that comes out of it is neutrons and protons, an occasional alpha particle, and what's left behind is nothing. The entire nucleus exploded. Under those circumstances, you talk about chipping? No, I don't think so. But that happens rarely because those extremely high energy cosmic rays are rare. When you're up in that range, the incoming cosmic ray has enough energy to produce extra particles, some of which are strange particles. So there's not a proton, not a neutron, a sigma particle, a lambda particle, a psi, and things like that, sigmas. Those strange particles were first found as cosmic ray secondaries long before we had accelerators that could make them.
So these findings of research were done in accelerators?
Eventually, what enables us to understand those strange particles was the accelerator work. But we had things like cloud chamber tracks that, here's a track. It looks like a negatively charged proton. How in the world can that be? There is no such thing as a negatively charged proton.
No.
Well, some of them were antiprotons, were legitimate negatively charged protons.
But
Some of them were strange particles that were sort of like a proton but had a negative charge.
But it acted based on the spin, right? The spin is part of that.
That's one of the things you look at is spin. In this particular case, spin doesn't tell you too much, but yeah, they will differ in spin.
Dave,
Yeah.
you know about the AMS experiment on the International Space Station, the cosmic ray detector?
No?
They put it up there, it was on the last flight. Andrew Feustel was one of the guys that installed it.
Yeah.
Like within the first few months of operation, it had 30 billion cosmic ray detections. 10% of them were antimatter cosmic rays.
Uh-huh. That's very interesting. That would not have, I certainly would not have predicted that. I have heard about that. But I would certainly not have predicted that only 90% were ordinary matter. And that's going to put constraints on a lot of the production mechanisms. A lot of the production mechanisms that we think were really important may be out the window if they are going to be required to produce 10% antimatter. That is weird.
Yeah, would antimatter cosmic rays make it as deep into the atmosphere?
No, they don't care.
No.
The
Okay.
bottom line is the atmosphere is doing a good job here.
Yes, it is. And that tells us something about space travel. It tells us that if we're sending, let's say we're going to hollow out an asteroid and go to another star with 50,000 crew members on this hollowed out asteroid, what are we going to have to do to provide for shielding against cosmic rays? The answer is we're going to have something between us and the cosmic rays that has a density in pounds per square inch of 14.7 pounds per square inch. How do we know that? Because right now we have 14.7 pounds per square inch of stuff above us, and we don't all drop dead from radiation sickness. So our own atmosphere presently is protecting us from cosmic rays, not completely, but adequately.
So on the space station, what are they doing for those folks up there now?
In detail, I don't know.
The Earth's magnetic field is protecting them.
That's an additional thing.
What is?
The Earth's magnetic field deflects most of the cosmic rays to where they come down in the polar regions,
Oh, okay.
and that's why you have auroras there.
Yep. Yep.
And the ISS is still in the atmosphere as well.
Yes, that's true too. But it's above almost all of it.
True.
And they
but it's still
also
enough
have
as we review.
limits on the cumulative time that any astronaut can spend out there based on their individual risk.
Yep. And there are different different guidelines for radiation workers and general public. I assume astronauts are considered radiation. I hope they're considered radiation workers because they're up there and they're working. And I have a funny story about that later on. I doubt if we'll have time, but you can read it and laugh.
So is this being looked at for the trip to Mars too? For
I presume so, yeah. Look, if people are prepared to volunteer for a one-way trip to Mars,
Oh, that's
then I don't think you're going to scare them away by saying, you might get cancer.
Might?
Yeah,
Undoubtedly.
yeah.
Yeah.
Well, one-way trip, you might prefer the cancer to the alternative.
Dave,
Yeah,
if I remember right, I saw a program where they were talking about making
they can't hear you.
I saw one of the programs where they were talking about going to Mars and having to have a special shelter built inside of the vessel or vehicle that actually had, I think it was water,
Yeah.
Water's
a
the
water
best.
liner.
Well,
Water's the best.
water is really not the best, but
One of
it's
the
the best thing that's drinkable.
Right.
And you need water anyway on the ship, so you might as well use the water as shielding.
Yeah.
We're 1/3 through, so we're making good progress. Let's drop the nuclear physics and start talking about the early Earth. I'm guessing that after 60 million years, the Earth had grown to 95% of its present size, that is radius, not mass. And after 120 million years, the Earth's radius was maybe 10 miles short of its present radius. Earth was, of course, still being bombarded from objects in space. I'm claiming that the big hits occurred so seldom after 120 million years that life could start up. But every time the Earth got hit by a larger than average thing, like the arrival of a 100-mile sized object, the Earth's biosphere would get heat sterilized all over again. And this probably happened many times. Life originated many times, got wiped out many times, but it's not as bad as you think, because we know from our experience in the kitchen that boiling biological tissues and even heating them above boiling in pressure cookers does not destroy the molecules necessary for life. Cooked food is nutritious. So that means after every wipeout, the whole Earth would be littered with just the biomolecules that are needed for a restart of life. So life is going to start a lot quicker than people would think if they didn't think about this pressure cooker thing. That's good food. They're scattered all over the Earth, all ready for life to restart. However, anything like the impact that created the moon would reset the clock to zero, really and truly zero, because it would drive most of the atmosphere off into space, so you had to reconstruct the atmosphere, would boil the entire ocean, might melt all of the crustal rock, might mix all of the molten crust down into the mantle. I don't think this littering of biological molecules is going to mean much when it's all mixed down into the mantle. So the clock has really and truly been set to zero. I'm guessing the last small wipeout that actually killed off the life on Earth might have happened about 500 million years after the formation of the Earth, 500 million years. And the sun was then a very young mid-sequence star, but more massive stars formed in the same cluster along with the sun had already evolved a good bit. A 3 solar mass star, 500 million years old, has already used up the hydrogen in its core, in the center of the core, has left the main sequence to become a red giant and ultimately will become a white dwarf. A 5 solar mass star of 500 million years age may have already exploded as a supernova. Maybe, maybe not. Because I don't know how much of the star's mass has been dispersed into space during its red giant stage and its AGB stage. A 9 solar mass star has gone supernova. It probably only took 25 million years to get there. At 25 million years, the Earth only weighed 1/3 of what it weighs now, so it's still collecting material from the accretion disk of the sun at that time. It's even likely that the first supernovas in the developing star cluster occurred before the sun's subcloud had even started to collapse. Massive stars evolve so incredibly fast, and the formation of a star the mass of the sun happens so incredibly slowly, well, incredibly by the same time scale. It seems likely that the material of the sun's accretion disk from which the Earth was made may have been seeded with material from one or more supernovas. And there's two things about that, two main things. One was, at the time when the Earth was formed, the cosmic ray flux was way, way greater than what it is now, because you've got all these supernovas recently occurred in the same cluster. And the other is, in addition to the cosmic ray flux, radioactive materials from the supernovas actually was part of the Earth. Now let's look at the geology of the early Earth. I'm claiming that the early Earth looked like 1/6 mountains, 3/6 continental shelf. So that means that it's covered over with salt water. So it looks like oceans. Like the Gulf of Mexico. The Gulf of Mexico is continental shelf. The Gulf of Mexico is not the ocean. It's salt water, but it's not the ocean. And 2/6 actual deep ocean. So it looks like 1/6 mountains and 5/6 salt water. Those numbers aren't significant for us. It's just interesting to have a mental picture of what might have been going on. At that time, 500 million years after the formation of the Earth, you've got already life living in the oceans. We call them bacteria. And they thrive near the mouths of rivers and streams, where eroded mineral nutrients are getting washed into the sea. They do not practice photosynthesis. Instead, they're getting their energy from concentrated nutrient elements in the river water. Here's an interesting thing. We're going to come to this in another page or so. This is a picture of what is among the largest bacteria known. These things are paramecium. Paramecium is a protozoan, you know.
Multicellular.
No, unicellular.
Unicellular is okay,
Yeah.
larger cell membrane.
And a paramecium is better than just one mecium, right?
That's true. That's true. They do reproduce by exchanging genetic material occasionally. A lot of the time they reproduce just by dividing, but occasionally they exchange genetic material, which is, technical term for that is sex. It has very little resemblance to what humans think of as sex, but
So they have a chance to evolve.
yeah, and that's a paramecium as opposed to one mecium. This thing, that thing is called, what is it called? It's not on this page, but anyway, it has a species, genus name and species name. And the DNA work says that this thing is a bacterium. Bacteria really are supposed to be like 1/10 as long as one of these things. And so in terms of volume of the cell, it's about 1,000 times smaller than a paramecium. And this thing is gigantic, yeah.
I found the name for it, boy. It's fission Wilsoni or something like that.
Yes,
Yeah,
that's more or less what it sounds like. I was going to make a diagram that showed some multicellular creatures too. And one of them would be about that big, little round thing. And that's the size of the mite that causes mange. That's way multicellular. That must have thousands of cells, or at least hundreds of cells. Another one is rotifers. Rotifers are even smaller. Rotifers are like maybe that big. Multicellular. So just because everybody, quote, knows that bacteria are tiny compared to everything else except viruses, just because everybody knows that single-celled organisms are smaller than multi-celled organisms, it ain't always true.
Where do you find this guy?
I forgot how that sound.
Sturgeon.
Right there.
What's that?
I was saying, it's right there. Yes,
It's
where do you
right
find this guy?
Oh, no, we found it. It's on the screen.
Sunscreen.
Now we know.
What do they do?
Okay. So these things live, oh, by the way, even at this early time, these things are being attacked by viruses. Well, these don't, because those are multicellular. But the unicellular things are being attacked by viruses already. The virus is not a difficult thing to invent. They invent themselves just by random changes in the DNA. So, and there are parasites that live on these things. And they do not swim around snapping their teeth. They just look like more bacteria. Instead of doing photosynthesis, nobody's doing photosynthesis yet, but instead of extracting energy from the difference in chemistry between the silty river water and the salty ocean water, which is what these early creatures were doing, instead of that, they're just basically finding dead bodies of the producer bacteria and digesting them, which is fine. Okay, what's this biosphere like without photosynthesis? Well, thermodynamics tells us that life cannot exist in an equilibrium environment. That, by the way, means that people who talk about rocks having lots of bacteria in them, I don't think so. At least not, the bacteria that are found in rocks can't be doing a lot of living because it's a thermodynamically uninteresting environment. A rock, the inside of a rock, there's no energy flowing through it. There's no sunlight hitting it. There's no changes in chemical composition. So the bacteria inside rocks, they must just be waiting for conditions to get more favorable. They aren't living inside there. They can't because of the second law of thermodynamics. So, well, let's see, I talk about sunlight a little bit, but anybody who's interested in sunlight can look up an astronomy book. But basically, sunlight is a dilute radiation flux. There's not all that many photons in the sunbeam, but the ones that are present have high energy. That's what permits life to occur on Earth. A small number of high energy photons in the sunlight. And that means that the sunlight is not in chemical equilibrium with the Earth's environment. That's good. Okay. Yeah, all right. Modern creatures use minerals also, like these early creatures did. But for those early creatures, the minerals were their food, their energy source. Humans today use minerals not as an energy source, because we got our energy from burning fats and carbohydrates and oxygen. Oxygen is the main energy source because without those you can't burn the fats and the carbohydrates. So those are our food, our energy source. Minerals and proteins, amino acids, we do not use primarily as an energy source. We use those as building blocks. That's what we're made of, whereas the sugars and the fats is where we get our energy from, our food. These early creatures, the minerals, were their food, as well as their building blocks. Okay, what about ancient sunlight? We're going to be interested in ultraviolet light and such. Well, we'll talk about what sunlight might have been like. Factory smoke, volcanic ash. No factory smoke, lots of volcanic ash. Dust storms. The early Earth, I think, was extremely dusty. Why? Because there's no roots of trees, and there's no branches and leaves that keeps the wind from kicking up dust from the ground. Dust storms today occur where there's almost no vegetation, or maybe no vegetation at all. So you can expect dust is going to be a major thing back then. What's the atmosphere made of? Well, I'm claiming nitrogen, carbon dioxide, carbon monoxide, argon, water, and maybe hydrocarbon smog. I mentioned that the books that used to say that ammonia and methane were major constituents of the early Earth's atmosphere, they were wrong. They were wrong from the beginning. They're wrong now. Back then they knew that anybody who thought about it way back 100 years ago could know that ammonia in the air is just wrong. It can't happen. The only way it can happen is if there's only no water on the Earth. If there's water on the Earth, the ammonia just goes into the water, gone. If there's ammonia in the air, it'd be gone within a week, let alone billions of years. And methane, no, can't exist back then. It existed temporarily, but no. I talk about how long would oxygen last on today's Earth with no plants, and it turns out it would last a long time. It wouldn't be gone like in 10 years. No, not at all. And you can look here and see what my reasoning is and what the numbers look like. I'm skipping down a lot. Carbon monoxide. I claim there's lots of carbon monoxide in the early Earth. Well, what's the implications for life in that? Well, carbon monoxide is not toxic unless you happen to rely on hemoglobin in your blood, which we do. Most organisms do not have hemoglobin in their blood. They don't have to worry about carbon monoxide. I'm skipping a lot here. Okay, how do you defend yourself against deadly sunburn? Well, that's ultraviolet plus the ozone produced by the ultraviolet light. And there's no ozone problem until there's oxygen in the atmosphere. And we're talking about a time when there wasn't much oxygen because there wasn't photosynthesis yet. So we're only interested in sunburn in the sense of ultraviolet light. Number one, there's no way to hide from the ultraviolet light. What you want to do is reproduce as frequently as possible. That way, if many or even most of your descendants get exposed to UV through events beyond their control, there will still remain many survivors who did not get exposed. Today, bacteria and some algae still use this strategy. The consequence of this rapid reproduction is, of course, that the body size becomes very small. How do you know the body size is small? Simple. It takes a long time to grow from that big to that big. So if you're going to reproduce quickly, your body size must remain small. And there's good reasons for wanting to have small body size as well. Another thing is you should be stationary. And basically what you want to do is secrete glue so that you will stick to sand grains and things like that, rocks. That way, those of your descendants who happen to be lucky and stick in places which are shielded from the deadly sunlight, they'll be able to thrive in that shielded location. Third, optical defense. An optical defense is make your glue black. And that's good. It's not really super effective, but it helps. And if you have a pile of many black-skinned organisms, at least the ones on the bottom are shielded from the ultraviolet light. People on the top of the pile, well, that's their problem. You can look for ultraviolet damage and fix it. Like DNA can have single strand breaks and thymine dimers. I don't know if both of those can be the result of UV radiation, but maybe. I wouldn't be surprised if both of them can be the results of UV radiation. And we know from modern DNA, not modern, DNA work done 50 years ago, that there are repair mechanisms for both of those damaged things that I just mentioned. Then, yeah, UV can create toxic molecules such as free radicals and oxidizing agents. So you manufacture free radical scavengers and antioxidants, which live in your body and bump into those bad molecules and take the hit and detoxify them. And finally, the brute force strategy, which won't work today, is arrange your biochemistry so that you do not rely on any molecule which can be damaged by UV light. That'd be fine if there were no other organisms around to compete with you, but all the high-performance molecules today are UV vulnerable. So you just would not be able to compete with the other organisms if you only had UV-proof molecules in your body. That's totally unrealistic. How much time we got?
10 minutes.
10 minutes, okay. Sorry about the vampire thing. I promised you vampires.
Yeah, I get it.
Yeah, okay. Basically, the vampire wants to avoid exposure to sunlight. You know about vampires. So I just thought it'd be fun to refer to the beach-dwelling vampire organism. And the organism does various things. It wants to be able to control its depth in the water, so you can float upwards, you can sink downwards. You want to make yourself sink, then you secrete a mineral crystal inside your body that's a lot denser than water and helps pull you down. To get up, you need to generate some gas. A gas bubble will pull you up. Basically, you want to commute between the surface of the water and the bottom, because at the surface of the water, or near the surface, you have access to atmosphere molecules, and which you don't have if you're really deep in the water so much. Down at the bottom, if you're really close to the bottom or in contact with the bottom, you've got access to mud and things like that, which have all kinds of cool minerals. And so ideally, you'd like to commute up and down. You want to go up to the surface at nighttime, you want to sink down to the bottom in the daytime. What's wrong with being up there at the daytime? You die. You're a vampire. So, I talk a little bit about eyes, I talk a little bit about sunscreen. How many people think that the eye came first before sunscreen? One. How many people think sunscreen came first before vision? One, two, three, four. Okay, sunscreen has it. I think I agree, because sunscreen is less of an invention than vision. What?
Vision is very easy to invent. A lot of simple creatures have.
Okay. I'd be interested to hear about that.
Something that's
I'm not a vision expert, so what do I know?
we have 100 different varieties of the eye. So.
Yeah,
Sunscreen isn't necessarily directional, so
that's true.
you
Vision,
develop sunscreen all over the place.
vision normally is directional. This is true.
Well, it seemed like sunscreen would be important because if these rays can damage stuff, then protection from them would be of more paramount importance than
Yeah.
being able to see.
Without vision, then maybe you're at a disadvantage relative to another creature that does have vision.
Yeah.
Without sunscreen, you're dead.
Yeah. Well, what about the radiation from something like kryptonite?
Kryptonite, that's not listed here. Like the flashlights? So, Krypton. Yeah. I talk a bit about eyes, how you might make an eye without a lens, etc. I have actually a reflective telescope built into this thing. Here's the mineral that ballasts the organism down, and you put your dye here, which is your light-sensitive object, light-sensitive molecule, on top of the crystal. This is a reflecting telescope because the top surface of the crystal reflects ultraviolet. And it's not a high-performance telescope. You can have an optical gain of no more than 2. However, getting an optical gain of 2 here is the equivalent of making your photochemistry twice as sensitive. That's dramatic. How you have to work really hard on the chemistry to make the photochemistry twice as sensitive. So it's worthwhile putting your photosensor on top of your ballast crystal. So I claim. Then I talk about more eye stuff. Little pun. It's made out of dye, and it's only one letter away from its goal, which is I. And then I complain, wait a minute, you're not allowed to say the word goal. That's a 4-letter word. We're talking evolution here. Evolution has no goal. So the organism does not have a goal of making an eye. The organism does not have a goal of making photosynthesis, no goal to make chlorophyll. All of these things were discovered accidentally by a lot of random mutations. That's my take on evolution. Well, I'm moving fast. I gotta turn the page. I didn't realize I talk about 4 different kinds of organisms, 2 plants, 2 animals, which I thought were interesting. And it turns out that making a well-designed sunscreen, once you've got a really well-designed sunscreen, you're almost at photosynthesis. And you can read this to see how I claim that might work. I'm not claiming that what I put down here is how it was done. I'm saying that what was done to get to photosynthesis might have been similar to what I put down here. And again, I made a mistake because I said what was done in order to get to photosynthesis. Not allowed to say that. This is random stuff. The organism does not have a goal of getting to photosynthesis. It's just that the organisms which, by dumb luck, happen to have mutations in their DNA that resulted in being close to photosynthesis, those organisms lived. The ones that made stupid decisions, again, accidentally, they died. No goal. Okay. We're just about done with that section. Now we can talk about radioactivity, and we've got 2 minutes.
About right.
Oh, we can do radioactivity in 2 minutes. Okay. I'm on the page that has Earth's radioactivity at the upper right. And at the lower right, I've got a chart. And the chart shows radioactivity now and radioactivity 4.1 billion years ago at age 1/2 gigayears. And I calculated how much radioactivity there is now on the Earth. And it turns out that essentially all radioactivity, the crustal radioactivity now, is due to 5 isotopes. One is rubidium-87, one is thorium-232, one is uranium-238, one is potassium-40, and one is U-235. Just 5 out of thousands of isotopes. And the total radioactivity in numbers which don't mean anything, but they mean something relatively to the other numbers, is 12,000 right now. At the early Earth, at age 500 million years, the crustal radioactivity, I claim, is 65,000, not 12,000. Interesting. There's a lot more radioactivity around back then. And back then, instead of having 5 isotopes being responsible, we've got 7. We've got samarium-146, which nobody ever heard of, and we've got plutonium-244, which is a moderately large contributor. Plutonium, there's no such thing as plutonium. That's an artificial isotope, artificial element. Well, not back then, it wasn't artificial. There was plutonium-234 lying around, 244 lying around. And then I talk about how I got those numbers and nuclear genealogy. Basically, to figure out what was around later on, earlier on, you look at what's around later on now, and you find isotopes that were created by the decay of the earlier ones that you're interested in looking at. And can figure out how much of the earlier ones were present. And so I did that. And I'm moving fast. Talk about family trees. If you're doing genealogy, you need family trees. And I showed 2 family trees here. And I'm getting close to the end because I'm skipping so much.
Unfortunately, we're right up against our
We're
deadline.
right up against the deadline. Okay. Anybody who has specific things to talk about, I will be at the, no, I'm not going to the meal because you gotta leave now. True? Okay. Well, is my phone number in front here? No, it isn't. Anyway, well, you can get my phone number from looking at our roster, right?
We're asking, we can,
We can
Well, excuse
disseminate, the officers can disseminate your phone number to
Okay.
this department.
Okay.
And it's fortunate now because he actually has a voicemail now,
You
which
can,
is astounding.
we can send you a-
This is true. Okay.
Thank you. Good job, Dick.
Well, it's been fun. I'm not sure if that's yours.
All right, so if those of you who've joined us for the first time wonder if it always comes with a handout, that's Dave's special style. So if you say join us for our next Macomb meeting where Jerry Dennifer will talk about telescopes, expect some eye candy to go with the lecture. So if you can join us at the Coney Island, we meet afterward at the National Coney Island on Van Dyke. So you take 12-mile road to Van Dyke, hang a right, and it's about half a mile north of 12 Mile. So we do meet there after every Macomb meeting. So unfortunately, our speaker can't stay with us, but normally we hash over things during the meeting. So.
If you have any questions about in the news tonight, there's still a lot of stuff here.
So I'd like to thank you all for joining us on this January. We've had a couple January meetings canceled because of bad weather. So this, we're happy to get through January without any problems this year. And thank you very much. And if you would take any of the trash that you've got on the way out, just want to be good citizens for the campus here.
Well done there, Diane, as always.
Thank you, Ken.